Hello everyone, welcome to my channel. Now in this video I am going to discuss two topics, magnetic flux and Faraday's law of electromagnetic induction from the chapter Electromagnetic Induction for class 12 students. Now magnetic flux, it is similar to the term electric flux in electrostatics. Now suppose you have an area. Now as we know, normally area is a scalar quantity, but in electromagnetism area is a vector quantity and it is always normal to the area being considered. So if for this area the area vector is normal to the area, so this is the area vector, and suppose this is the direction of the magnetic field for this particular area. This is the direction of the magnetic field. So angle between magnetic field and area vector is theta. Then magnetic flux linked with this area, magnetic flux phi b, magnetic flux linked with this area, it is given by the expression product of b cos theta into A, or it is b into A cos theta. Now see, b cos, this is b cos theta will be in this direction. That means we are taking that component of magnetic field which is in the direction of area vector and normal to the area. Similarly, if I take b into A cos theta, so you are taking that component of area vector. This is A cos theta will be in this direction. If this is A, this is B, this is theta, so this is A cos theta. So that means now you are taking that component of area for which the magnetic field is perpendicular to the area. So that means when you are saying magnetic flux, we are counting those magnetic field lines which are passing perpendicular to the area being considered. This magnetic flux is a scalar quantity. Magnetic flux, it is a scalar quantity. Phi b, it is scalar quantity. Though magnetic field and area vector, they are vector quantities, but magnetic flux is a scalar quantity and it is expressed as dot product of magnetic field and area vector. Okay. Now the unit of this magnetic flux is Weber. So this is for 1 Weber. Magnetic field is Tesla. So 1 Tesla to 1 meter square. When B and A, they are in the same direction, for theta is equal to 0 degree. Okay, and the dimensional formula for magnetic flux, it is m L square T inverse 2 A inverse 1. Okay, so this is magnetic flux. Now later we will see in this chapter that how the change in magnetic flux produces or induces an EMF, and this observation was made by Michael Faraday. So we have the Faraday's law of electromagnetic induction. Okay, so what this law says, that the EMF induced, it is directly proportional to the rate of change in magnetic flux. EMF induced in a circuit is equal to the rate of change of magnetic flux linked with the circuit. Okay, so this proportionality constant is 1. So this is E is equal to d phi by dt. Okay, so this is EMF and this is the rate of change in flux, rate of change in flux. Okay, the magnetic flux. So this is Faraday's law of electromagnetic induction. Though Faraday, he gave a relationship between the induced EMF and the rate of change in magnetic flux, he did not give any information with regard to the direction of flow of this current as a result of this induced EMF. Now, let us see one more relation related to this Faraday law. If R is the resistance of the coil in which this flux is changing, so in that case E is equal to I into R. This I is the current and R is the resistance of the coil. Okay, so in that case I can write this as I into R is equal to I into small r is equal to R is the resistance is equal to d phi by dt. Now what is this I? If Q is quantity of charge flowing through the coil, I is dq by dt. So this gives R into dq by dt is equal to d phi by dt. Okay, so that gives dq is equal to d phi by R. R is the resistance. Okay, so if I integrate this, so the flux changes from initial flux phi I, so phi f, the charge flows from 0 to Q. So this gives Q is equal to phi f minus phi A divided by R, the resistance. So this amount of charge will flow through the coil. Now the interesting point is this charge flowing through the coil depends on the change in the flux and the resistance, but it is independent of the way the flux changes. Whether the flux changes very quickly or very slowly, it is independent of the way the flux changes. It only depends on the change in flux. So I can write this as Q is equal to delta phi by R. So this amount of charge will flow through the coil. So this is Faraday law, and this is the implication of Faraday law of electromagnetic induction.